Alright, hello class. Today in this particular video we're going to be looking at a change of variables in multiple dimensions. So I like to think of this as generalizing u-substitution into multiple integration. So I often think of this as basically uv-substitution versus just u-substitution. Right, because when we have, say, more than one dimension, we can actually have, say, x and y both be in terms of u and v, or vice versa. All right, now where this comes about is situations where either the limits of integration are really complicated, or the integrand itself is really complicated, can't be integrated, or both. Okay, so for example, imagine this integral here, say the double integral over r of e to the x squared plus y squared dA, where r is the unit circle. So there are two big issues here. One is for the unit circle, whether we think about it as going bottom to top or left to right. So I'm going to do bottom to top. Well, the unit circle is the formula x squared plus y squared is equal to 1, okay, which if we solve for y, gives us y is equal to plus or minus the square root of 1 minus x squared. Okay, so the bottom piece is y equals the negative square root of 1 minus x squared. Okay, so that's the bottom. Then the top, right, that's y equals the positive square root of 1 minus x squared. But here's the issue. If we think about this as going from bottom to top, when we set up this integral, well, we're going to have the integral from, our x's are going from -1 to 1. Then our inside integral is going to be going from y equals the negative square root of 1 minus x squared to y equals the positive square root of 1 minus x squared. And the integrand stays e to the x squared plus y squared. So this will be dy dx. So the problem here is twofold. One, these limits on the inside are awful to deal with. But also, there's no integral rule for this. It doesn't matter what order we choose. This integral can't be done explicitly. Okay, so that's one motivating factor. Essentially, the integrand is really disgusting. That might be one way. And that's our typical motivating factor for normal u-substitution. It's that the integrand is really complicated, but we can actually simplify it down quite a bit. Or, like I said, it could be the limits of integration, or the region that we're trying to integrate over, is really disgusting. For example, suppose our region that we were looking at looks something like this. Okay, so suppose R is the region bounded by the hyperbolas xy equals 1 and xy equals 4, and also the lines y equals x and y equals 3x. Well, these hyperbolas, if we solve these for y, we'll get y equals 1 over x and y equals 4 over x. And so let's take a look at a graph to see what this region would look like. And for simplicity, let's just suppose everything's positive, right? Or at least non-negative. All right, so we're basically just in quadrant 1. Okay, so here's the graph of all these curves. In quadrant 1 here. Here's the two lines. Okay, and here's, say, y equals 4 over x and 1 over x. Okay, so if we look at the region bounded by all of these, So if I fill all that in, we have this region in here is our R. Okay, and if we zoom in on this, yeah, this is good. What you can see is that if we tried to set this up in Cartesian coordinates, right, as a double integral, if we thought about it in terms of bottom to top, what you'll notice is you see here, whoops, at this point, that's where the bottom would change. If you're going from left to right, here's the bottom from left to right, but then here it changes, but the top doesn't. Okay, but the top changes here. So they don't even line up. So we would need an integral for here, an integral for here, and then an integral for here. So it would take 3 integrals to set this up. Okay, then if we were thinking about it left to right, it's the same thing. The left side changes when we move here, but the right side changes when we move here. So we would need an integral for this bottom piece, an integral for the middle piece, this thin little middle piece, and an integral for the top piece. So in this situation, an integral over this R, no matter what way we oriented R, it would take 3 integrals to set up with pretty nasty looking limits. Okay, so our UV substitution is to help us avoid situations like this. Okay, so just to reiterate, no matter what order or orientation we choose here, integrating over R will require 3 separate integrals, and we never want that if we can avoid it. Okay, so this leads us to change of variables, a UV substitution. All right, to write it in a sort of general terms, suppose we wish to transform the double integral, say over R, which I'm saying is in terms of x and y, of f of xy dA, in terms of x and y, into an integral with respect to 2 new variables u and v using the transformation x equals a of uv and y equals b of uv. So what's happening here is, say we have some sort of problematic region here, R, and this is in x and y. Okay, but using a transformation, and typically we give it a name, say t. Okay, so this is the transformation t, which is x equals a of uv and y is equal to b of uv. The hope is that it moves it into a new coordinate system, say u comma v, and the region itself will be much simpler, say just a rectangle. Okay, so this would be, say, S. Okay, so we can do this, and it's done in this way. So suppose this is what we want to do, then, right, our double integral over R of f of x, y, dA of x and y. Okay, I'm putting that there so things are sort of more specific. This double integral ends up being a new double integral over S of f of a comma b, okay, times the absolute value of j of uv, and I'll explain what this is in a minute, dA uv. Okay, in other words, what's happening is we have a double integral over R of f of xy, say dx dy. It doesn't have to be in this order, but I'm just generalizing here. And we can turn it into an integral over S of f and of a, b. And this is actually going to be a function of u and v now. So we could actually rewrite this as capital F of u comma v times something here, du dv. Okay? Where j of u comma v is the Jacobian, right, of the transformation defined as, right, so j of u comma v, sometimes this is given as partial xy over partial of uv, because what it's doing is essentially telling you how to get this. It's the partial derivatives of x and y with respect to u and v. We put it in a matrix such that it's the derivative of x with respect to u, the derivative of x with respect to v, derivative of y with respect to u, the derivative of y with respect to v, and we take the determinant of that matrix. So we'll have the derivative of x with respect to u times the derivative of y with respect to v minus, now the opposite diagonal, the derivative of x with respect to v times the derivative of y with respect to u. Okay, so this right here is what goes in this absolute value. The reason it's an absolute value is mainly so we can set this up however we want. We can set it up in whatever order we want, okay? And the negative should come out, if there is a negative that should be there, it will come out in other places. We try to avoid it here. Okay, so this is probably pretty abstract and funky looking, but all I want to show is that this is what we've been doing all the time with u-substitution. We just haven't quite written it this way. All right, let's take a step back to our Calculus 1 days, and let's look at an integral, say x e to the x squared, and we'll look at this from, say, 0 to 1. All right, and when we so we've been doing quick u-substitution in my videos since the Calculus 2, but instead, let's actually do a full u-substitution. So to do this problem, typically what we would do is we would let u be x squared, then du would be 2x dx, and we'd say divide this over, so that we would have 1/2 du is equal to x dx, right? And here's our x dx together, so that would be 1/2 du, and here's simply our x squared, so that would just be u. And so when we make the transformation, we'll get the integral e to the u times 1/2 du. And then we would have to change the limits. So actually, let me make this 0 to 2, so it's a little more obvious what's going on. So when we put in 0 for a lower limit, right, u of 0 will be 0. Okay, and when we put in 2, we'll end up with 4. Okay, so we changed what we had here, which were x limits, right, into u limits, and we changed the whole integral into u, right? So we'll have the 1/2 times the integral from 0 to 4 of e to the u du. All right, so what I'm trying to get at here is that this 1/2 is essentially what we had in the previous slide here. That is that j. Okay, that's essentially the Jacobian. Okay, so this is essentially J, right? So whenever we did U substitution in the past, there's always stuff left over. All right, so just remember there's always stuff left over when doing U substitution. And for UV substitution, that leftover stuff is the Jacobian. In fact, to show you what I mean, if this was, say, if instead of doing it this way, because if we look back again at this last slide we had, where was it? Here it is. Our transformation was an x in terms of u and v and a y in terms of u and v. Instead of the other way around, how we usually do it is a u equals something. Okay, so instead of doing u equals x squared, we could do this integral just the same by letting x equal the square root of u. Okay, then the derivative of x with respect to u will be 1 over 2 square root u, and then we can plug this in, because this would essentially be our Jacobian. Right, because all we have here is u. Okay, so if we were to plug this in now, the x would become square root u. X squared would become u. The dx, that would become j, absolute value du. Well, here the j is this 1 over 2 root u du. Okay, then when x is equal to 0, this will tell us that u is equal to 0. And when x is equal to, I did it again, that should be 2. When x is equal to 2, we'll get 2 is equal to the square root of u, telling us that u is equal to 4. And then here is the leftover stuff. This is the Jacobian. Okay, but in this case, the square root u terms cancel, and we get the integral from 0 to 4 of e to the u times 1/2 du. Okay, so this is just to show that this idea, this Jacobian thing, we've been doing this whole time. It's just a lot simpler when we're dealing with just u substitution versus uv substitution. Okay, so let's actually look at this in an example with multiple dimensions and see what we see. Alright, so let's evaluate the double integral over r of the square root of y squared minus x squared dA, where r is the region given by the graph of this diamond here. It's the diamond with vertices 0, 0, 1, 1, 0, 2, negative 1, 1. Okay, now I'm going to say that we use the transformation u minus x equals u minus v and y equals u plus v. Okay, all right, so the first thing I want to show is why we would want to use a uv transformation. It has a lot to do with the fact that this graph, okay, the inside of this diamond, no matter how we decide to set it up, whether it's bottom to top or say left to right, there's a point in either direction where say the bottom and tops change or the left and the right changes, right? Because say this graph right here, this corner, or not really corner, but this leg, I guess I could say, is the line y equals x. And this leg here is y equals negative x. Then this leg is y equals, the y-intercept is 2, so it'd be 2 minus x. And this is the line y equals 2 plus x. Okay, so what would happen is on this side, this line is the bottom, but when we move past this point, this line becomes the bottom. Right, so we're going to have to put or set this up with two integrals. And not only that, this integrand is not going to be that easy to do. Just looking at it, honestly, if I don't use a u substitution, it looks as if that might have to be something like a trig substitution, right? And we definitely don't want to do that. So we're going to use a uv substitution using this transformation. Okay, so there are a few things to get this going. One, this is our r, right? We need to find s. And this is where this becomes a bit of a puzzly piece. Okay, so let's start here. I'm going to call this, I'm going to put this in yellow. And so I'm going to look at the y equals x line. Okay, in yellow. And then I'm going to replace the y and the x with their transformed versions. Right, so y is u plus v, and x is u minus v. Right? And so now the u's cancel on both sides, and I can move this v over to get 2v is equal to 0, so we get v is equal to 0. Right? So I'm going to set up a new axes over here. This is going to be the uv axes. Okay? So v equals 0, that's a horizontal line here. Okay, so here's v equals 0. All right, now I'm going to take the next line. Let's say it's this one. Color it in green. That's y equals negative x. All right, and we're going to play with this one. The y is replaced by u plus v again. And then it will be negative x, so it's negative of u minus v. So we get, on this side, negative u plus v, and u plus v on this side. So now it's the v's that cancel, and I can move the negative u over to get 2u equals 0, so u equals 0. So u equals 0 on this graph is this vertical line on the axis. Okay, so here's u equals 0. Okay, next up, let's do 2 plus x here in blue. All right, so y equals 2 plus x, so the y is always this u plus v, and then it will be 2 plus x, which is u minus v. So once again, the u's cancel. This negative v comes over to give me 2v equals 2, so we get v is equal to 2. So v equals 2, that's going to be something like this horizontal line here. Okay, and then finally, let's color this one up in red. This is y equals 2 minus x. All right, and that's going to give us a u plus v for y, like always, and then a 2 minus u minus v. All right, so we'll get u plus v is equal to 2 minus u plus v, and now it's the v's that cancel, and we'll get 2u is equal to 2, so u is equal to 2. Okay, something like this. So, the region bounded by all of these guys is this rectangle here. Okay, this is our S. So what we've done is we've, with this transformation, changed the diamond into this rectangle. Okay, now I've cleaned it up a little bit, but as you can see, what we've kind of done is, and I'm sorry, I just realized here I did some, forgot to divide. These should be 1s. I don't know what came over me there. All right, so what we've essentially done here is turn this diamond into this square. Okay, there, I made it a little more square-like. You can almost see that all we've done is essentially tipped this down. Like, let it fall to where the yellow side was on the bottom. Okay, this is going to be a much easier integral to deal with because, well, the limits of integration over S are just going to be 0 to 1, 0 to 1, no matter what order we do them in. Whereas here, our limits are going to be kind of gross, and they're going to be different depending on what order we look at them in. Okay? So, there's our limits taken care of. We found our S. Right? Now, we need the Jacobian. Okay, so now, Jacobian. So J of uv, which I'll write again, partial of xy with respect to uv, it essentially just tells you how to set this up. And I want to specify here, the order you do this in doesn't really matter. You just need to stay consistent. So if you say that you're going to do partial x with respect to u, and then you put an xv here, that means this is the u column, and this is the v column. This will be the x row, and this will be the y row. You don't have to do it this way, but you have to stay consistent. However you decide to set it up, you have to stay that way. Okay? So, let's put these in. Just to remind you what our transformation was. Right? X was u minus v, y is u plus v. Okay, so the derivative of x with respect to u, well, it's going to be this derivative with respect to u, so that's going to be 1. And the derivative of x with respect to v, that will be negative 1. The derivative of y with respect to u is going to be 1, and the derivative of u with respect to v will be 1. Okay, and then we just take the determinant of this matrix. So we'll get 1 minus a negative 1. So we get 2. Okay, now the final thing we need to do is we need to take our f of xy and move it into the f of a comma b. Okay, in other words, our x was u minus v, so this is going to be f of u minus v, comma u plus v. Okay, so f of xy was, we might forget now, it was way up here. it was the square root of x squared minus y squared. All right, so we're going to write that. Oops, had that flipped. All right, so when we put in u and v into this, so our y was u plus v all squared, and then minus x, which was u minus v all squared. All right, so we're going to get the square root of u squared plus 2uv plus v squared when we FOIL this guy out. Then it will be minus u squared minus 2uv plus v squared. All right, and based on what we have here, since we have a minus, make sure you apply it to each piece, but because of that, our u squareds will cancel, our v squareds will cancel, and then we'll get a 2uv plus a 2uv, so we'll end up with the square root of 4uv, or 2 square root uv. Okay, and so now we have all the pieces we need to finish this problem off. I know it seems like a heck of a lot of work here, but we're almost done. All right, so the double integral over r, the square root of y squared minus x squared dx, comes out to be the definite integral from 0 to 1 and 0 to 1. It really doesn't matter what order we go in because it's the same limits either way. Of the integrand becomes 2 square root uv, right? Then absolute value of 2 du dv, right? So this is our f of ab, and this here is the absolute value of the Jacobian of uv. Okay? Now, I'm just putting the absolute value here to be very careful. Just note, if your Jacobian's ever negative, you can just, ignore that. All right. Now, we have a fairly simple integral to calculate here. It's essentially integral from 0 to 1, integral from 0 to 1 of 4 u to the 1/2, v to the 1/2, du dv. Right? And we can just start by taking the integral with respect to u, right, which u to the 1/2, its integral is going to be 2/3 u to the 3/2, and then v times, or v to the 1/2, because remember the v isn't changing here, u going from 0 to 1. Okay, and when we plug in the 0 and 1, what we end up with our fundamental theorem of calculus step is simply, well, 1. Because when we plug in 1 to any power, that's just going to be 1. And plugging in 0, it's all going to disappear. So we'll end up with 8/3 v to the 1/2 dv on the inside. And now we can integrate again. We'll get the 8/3 times 2/3 u to the, v to the 3/2, and we'll evaluate that from 0 to 1. All right, which will then come out to be, since we're just plugging in the 1 and the 0, 16/9. All right, so that one was probably a lot of going on there, and there is. Right, we have to transfer the r to s, we have to find the Jacobian, we have to transfer f of x, y into some function of u and v. But like always, if you just take it a step at a time, okay, hopefully it will just work out for you, because like a lot of situations, each particular piece maybe isn't so bad. as long as you take it, a step at a time. All right, enough blabbing from me. Let's take a look at another example. All right, so for this example, let's evaluate the double integral over r, v to the x, y, dA, where r is the region bounded by y equals 1 over x, y equals 4 over x, y equals x, and y equals 3x. This is essentially the example we looked at earlier. Let's see if I still have the graph at the ready. Yeah, it's this region here. Okay. All right, so the reason we would want to use a UV substitution here is mainly, it's not because the integrand is nasty, it's because these limits are nasty, and as we established last time, this would require at least 3 integrals in any direction that we decided to look, so that's definitely not ideal. All right, so let me show you the transformation that we're going to use here. All right, so we are going to use the transformation x equals u over v and y equals v times u. All right, and for simplicity, suppose everything is positive. Okay, and that'll come into play later. If you're curious to where these transformations come from, for a lot of these, you're just going to be given the transformation. I will talk about in a little bit how you find these transformations. Okay, but for right now, it's more important that if you have a transformation that you know how to use it. Okay, so let's start using this transformation. So we have and let me pick a different color for one of these, like a red. There we go. All right, so I already have sort of a setup of colors here that I can match or map to the UV. So here is, let's start with y equals x in orange. Okay, so y equals x. Well, again, we plug in the y, which is v times u, and the x, which is u over v, and then we try and solve this. And if I move the v over and the w over, we'll get v squared is equal to 1. So v is equal to plus or minus 1, and since we are assuming everything's positive, v is going to be 1. Okay. All right, so here it is on a graph. Here's the UV axis. V equals 1 is this horizontal line. Okay, the next line here in red is y equals 3x. So for y equals 3x, we do this same thing. We'll have VU is equal to 3 times u over v. Well, the only thing that's going to really change here is that we'll get v squared is equal to 3. So we get v is equal to plus or minus the square root of 3. And again, we choose the positive one because we're assuming everything is positive here. Okay, and v equals square root of 3. Here's that graph here. Looks something like this. Okay, square root of 3 is about 1.7, so a little above the v equals 1. All right, then if we go to our graph again, we're going to choose one of these parabolas. All right, and the one in green is 1 over x, and I know that because if I plug in 1, I get 1. So this is y equals 1 over x. Okay, and that's what we start with, the y equals 1 over x, and then we replace what we have. Y is v times u, and x is u over v. So I have 1 over u over v. So when we invert and multiply, or if we just multiply this over as is, we'll get VU times UV is equal to 1. And here the V's will cancel, and we'll get U squared is equal to 1. So U is equal to, I'll just go ahead and skip the plus and minus part because we're only picking the positive guys. And we'll get U is equal to 1. Okay, here we go. On the UV axis, U equals to 1 is this vertical line. All right, and then we have one more to go, and that's this one in blue here, which is the Y equals 4 over X, sorry, because if we plug in 1 here, we get 4. So this one in blue is Y equals 4 over X, which, plugging this in, we get the same idea here. VU is equal to 4 over UV, so we get the same thing happening. VU times U over V is equal to 4. The V's cancel, and we get U squared is equal to 4. So U is equal to 2. Okay, so we get the line U equals 2 here, and the region bounded by all of these lines is this one here. So this is our S. And the beautiful thing about it is we've now taken this horrible region here, right, this strange looking thing here, and we've turned it into a rectangle. All right, and that is often our motivation here, is to try to take something super complex and turn it into hopefully a rectangle or a triangle or something real simple like that. Rectangles are the best because that's just constant to constant. Okay, so next we're going to find the Jacobian. Okay, which will be J of UV. All right, and again, I always write it out, the partial of xy with respect to UV. And I'll write it a little differently this time. It's going to be x sub u, actually, I could do it this way. X sub u, y sub u, just to show that it doesn't really matter what order we go in. Then x sub v, y sub v. So here we instead did an x column, a y column, a u row, and a v row. And again, doesn't matter. That's why we incorporate the absolute value. Okay, so the derivative of x with respect to u, well, the 1 over v is a constant, so it's just going to be 1 over v. Right? The derivative of y with respect to u, well, y with respect to u, that's just going to be v. Okay. Derivative of x with respect to v, well, now it's the u that's the constant, and the v that's in the denominator is the variable, so this is going to be negative u over v squared. Okay, and then y with respect to v, that's simply going to be u. Okay, so we take the determinant of this matrix, be the main diagonal times the, the main diagonal minus the off diagonal. So it will be u over v minus a negative uv squared times v. Okay, and here the v's cancel, and we get a uv plus uv, so we're going to get 2 uv. Okay, so there's the Jacobian. Now, when I put that in the formula, I'm going to throw in an absolute value, but since everything's positive, we don't have to worry about that here, but still just to be as specific as possible. Then, finally, so there's the Jacobian. Now, we need to find the f of a comma b, right? So, xy, well, f of xy is e to the xy. All right, and now we just plug in the the x, which is uv, so this will be e to the u over v, times y, which was v times u. Okay, so the v's cancel, and this comes out to be e to the u squared. All right, so now I think we actually have everything that we need to finish this off. So the double integral over r of e to the xy dA is going to be, all right, it'll be the double integral of e to the u squared times the absolute value of 2u over v, and we can choose whether we want to do dv du or du dv simply because we have a rectangular region. So I'm just going to do du dv. Okay, and what we found was that u goes from 1 to 2, and v goes from 1 to square root 3. All right, and now we are ready to go. Let me rewrite this a little bit. All right, all I did really is drop the absolute value bars here and join the u's together and the v's together, okay, because they're nice and separated, which is perfect. Now here, this will be a quick u substitution. And it's nice we know that now because that's really going to simplify our life here, especially now that we've had to do all this work to get here. The v integral I'm not going to mess with. That'll still be 1 to root 3. And then here the 2u will be left alone. It'll be e to the u squared. All right, the integral of e to the stuff is itself. Then divided by the derivative of the stuff with respect to u, so that will be 2u. Okay, which those guys cancel. And then we will evaluate this from u equals 1 to u equals 2. And notice out here I've put the 1 over v dv. Why? Because it doesn't actually affect us that much here. Okay, since there's no, I mean, we could put it in, we could not. It doesn't. It's not going to really change our work here. So this will be e to the 4th minus e to the 1, so e to the 4th minus e, okay, times 1 over v dv. Okay, and now the integral of 1 over v dv, this is just a constant, so this is going to be e to the 4th minus e times the natural log of the absolute value of v from 1 to the square root of 3. All right, so it will be e to the 4th minus e, okay, then times will be the natural log of root 3 minus the natural log of 1. Notice I dropped the absolute value because these guys are positive. Natural log of 1, well, that's 0. All right, and natural log of root 3, well, we could actually take that out as 1/2 if we want to. It doesn't really matter. If you look it up in the back of the book, it might actually do that. So probably the most simplified version of this you could probably ever see might be something like e halves times e cubed minus 1 times ln 3. Okay, but again, who knows? I think just e to the 4th minus e times ln of square root 3 is also good enough. All right, so that is pretty much what is going on when we try to do a coupled UV substitution. Now, I'm going to call it here for this particular lesson. However, I'm going to also make an extra video to kind of show you where this Jacobian idea comes from. And it's for those of you who are actually interested in seeing like where the J shows up and why it shows up. Okay, so we will look at that next time, but other than that, that should definitely be enough to get you rolling on the homework, and I will see you all in the next one. Cheers!